In order to analyze the impacts of a spill or leak on groundwater, a scientist will need to analyze the topography of the area. They may start by obtaining a standard topographic or contour map of the site area. Elevations at the Earth's surface are depicted on topographic maps by means of lines of equal elevations called contours. So these contour lines are going to then indicate areas where we have equal elevations. The vertical distance between adjacent lines are called contour intervals. Now let's say that we want to construct a topographic profile from point X to point Y on this map. The distance from point X to point Y is going to be our horizontal distance. So in this example, the distance between point X and Y is about 6 miles. So if we place a strip of paper over our topographic map and we place a mark wherever our strip crosses our contour lines, we're going to then have a way for us to determine the elevation as we proceed over distance. So now we have the elevations of all the key points along X to Y. We also know their horizontal positions relative to each other on the topographic map. So we can now construct a two-dimensional representation, basically a profile of what the land slope looks like in this field. So if we set up a simple graph and then establish a vertical scale to represent the land elevations. Any vertical scale will do, but usually this scale is going to be exaggerated and doesn't actually equal the horizontal scale. So we put this strip of paper with our marked elevations along the bottom of the graph, and then we'll draw a line up from each elevation mark on the strip until it intersects the line on the vertical scale that has that same elevation. So at point X, we were at 110. At our first mark, we were at elevation 100. Then we were at elevation 90, elevation 80, elevation 75, elevation 70, elevation 60, elevation 55, and elevation 50. Now, if we connect these dots, what we're going to see is the slope of the area. And so we have a basic topographic profile. Now, topographic profiles provide geologists with the slope and a general view of the land, as seen from a particular line on the ground. A geological cross-section, on the other hand, provides more detailed picture of the regional geology and the specific rock types and structures present at and below the surface. So let's assume that we stop along a road to view a rock outcrop that we think is pretty interesting. We want to sketch the outcrop so that we can show it to a friend back home. So you sketch a drawing of it and you label the rock types that you see. While at the outcrop, you get a good idea of the rocks and the soil in the region. The rock is solid granite and the soil on top of it is sandy. So we're going to plot the location of this particular outcrop on a road map so that we may visit it. Now, during our drive in the area, we notice that the areas along routes 5 and 10 west of our outcrop location have granite at the surface. So we have granite at the surface. And there's no overlying sandy soil, just bare rock. However, to the east, along Route 10 and along routes 20 and 30, the land is quite flat and you see only sandy soil at the surface. You mark these observations on your road map, but where's the granite on the eastern portion of the map? It's likely below the surface someplace, but how far? So one way that we could obtain subsurface data is through drilling. So oil and water drillers will actually monitor how deep they drill and record the soil and rock types and thicknesses that they find at various depths. So you suppose that you find that a driller had to drill through 40 feet of sandy soil before hitting granite when putting a well at point Z. So we had to go down 40 feet here. So you now know that 40 feet of sandy soil is overlying the granite at point Z. So from our observations at the original outcrop You know the thickness and trend of the sandy soil at the outcrops at point A and B, so we can determine as we travel along Route 10 that the granite surface is actually sloping below us and is about 40 feet below the surface. Now, if we plot the surface distribution of granite and sandy soil on the map, we can construct a simple geologic map. This map will tell us the type and position of rock and soil at the surface. Now, to find out what's taking place below the surface, we'll need more data to construct a true geologic cross-section. Fortunately, we have several other wells that have been drilled in the area at locations 1 through 4. From the well data, we know that the depth below the surface to the granite body at each location. So for the sake of simplicity, we'll assume that the surface is the same everywhere, 1,000 feet. At well 1, our granite is going to lie 10 feet below the surface. At well 2, it's 20 feet below the surface. At well 3, it'll be 30 feet below the surface. And then at well 4, the granite is 40 feet below the surface. From this information, we could definitely see that the granite is sloping to the east. And from the elevation measurements, we can also tell the thickness of the sandy soil. So originally, we made a simple geologic profile of this original outcrop, but it wasn't drawn to scale, but it gave you a rough idea of the geology of the area. When solving a groundwater problem, we want a more accurate cross-section. To do this, we're going to use the same basic principles that we use to construct a topographic profile. To begin, we'll lay a strip of paper on the geologic map and mark a few key land elevations on the map. For example, the granite elevations at the surface and the granite elevation of the sandy soil at the surface. We'll then plot the elevation of the granite at the surface and subsurface in each well. For example, the granite at well 1, as we said, was 10 feet below the surface at an elevation of 990 feet. So we'll proceed as before to construct a basic topographical profile. Only this time, we're going to be plotting both the surface elevations and the depth elevations to granite on the same graph here. So if we begin, we know that at point X, the granite was 960 feet below the surface, which 960 feet below the surface, which was at 1,000 feet. Then at our first place where the granite kind of disappeared, that was at 1,000 feet. Then we hit granite at well A at 10 feet down, so we'll be at 990 feet. Then at well B, we were 20 feet down. At well C, we were 30 feet down. And at our final one, we were 40 feet down at 960 feet. So if we connect the line here, we're going to actually get a nice cross-section of the geology that shows the depth of granite from the surface all the way down. So we know this is our granite outcrop, and then over here is going to be all our sandy soil. For your lab, they've actually completed the topographic profile for you. And so you'll be asked to then complete that geologic cross-section so that we can see the location of the major layers of soil types and then make some inferences on how that groundwater is going to move and how the oil spill in particular is going to impact that particular groundwater source.